It's extremely nice to see so many people here. It's even filled up on the sides here. My name is Martin Jakobsson, or Martin Jakobsson in Swedish. I'm from Stockholm University. I'm a professor of marine geology and geophysics. So that means that I'm also a geoscientist, which I will speak a little bit about. But I will start. First of all, I have the honor to open and close this session today. And I will start with saying a few words about the Crafoord Foundation, which actually is the reason why we gathered all here. The Crafoord Foundation here in Lund was established in 1980 by Holger Crafoord. And the whole objective with the foundation is to support science and education. An extremely important part of Crafoord Foundation is that it awards the Crafoord Prize. And for us who are in the sciences that you will see down there, or actually I should point up here, it's equivalent to the Nobel Prize in this science field. So it's an extremely important award for all of us and world recognized. So the Crafoord Foundation gives out the prize in mathematics and astronomy, in geosciences, in biosciences, and in polyarthritis, which is a rheumatism in Swedish. And before I move on to introduce the main attraction today, the speakers, I will just say a few words about geoscience, because this year's Crafoord lecture, it's in geosciences. And I know that you are not studying geoscience as a subject in school. It comes a little bit here and there. And as a geoscientist, I think that's too bad. I would really love to see it, and I'm going to tell you why I think so. So geosciences, it's the science or geovetenskap. You will also hear earth science if you listen to international, or what we say sometimes in English. It's a science that encompasses the whole earth. We are studying the hydrosphere up here. I should maybe start saying what I have here. The atmosphere. Well, we studied the composition of the air and of particles, pollution, etc. We study the biosphere, all living material on Earth, and we're studying the hydrosphere, which is both frozen and liquid. So the water in the ocean, fresh water, all of that components, and we also study the solid Earth, which we lap together into geosphere. So in geoscience, you're really using the components that you learn in school. We study it by using physics, chemistry, biology, and mathematics. So it can be extremely mathematical, it can be less mathematical, because it's such a broad scientific field. We really need geoscientists, and I'm trying to make a pitch for that. And why do we need it? Well, we need to know how the Earth is composed, what it consists of. We need to understand, for example, climate. Everybody here would know how important that is, and that's a little bit of a topic of today's lectures, because we need to make better predictions of future climate change. We also need to make much better prognosis of future sea level rise and all these things that you hear in media. That's geoscientists that work with that. We also need to understand the mechanism behind natural disasters, earthquakes. We need to make much, much, much better predictions of earthquakes when they happen. Today, we cannot predict within a few days or a week when an earthquake is going to happen. We can tell that it will happen in a long time in certain zones, but we are very bad in predicting closer up to when it's going to happen. We need to make better tsunami propagation models so we can warn when tsunamis are coming and all these things. And lastly, there are so many different components of earth science or geoscience, but lastly, what I mentioned here is that we need to know all our natural resources, specifically now when we're moving over into a more sustainable economy or sustainable use of earth resources. That's also what geoscientists are studying. I don't know if you ever heard about the United Nations Sustainable Development Goals. These are goals that the United Nations have come up with, that we should use the earth in a much more sustainable way, which is very important. And within these goals, geoscience will fit into many, many, many of them. I'm a geoscientist, and just to give you a flavor of what we do in real life, I just come back from an expedition to northwest Greenland, all the way up to the very, very top here. And you might not know, but there are white spots on Earth which no one ever been to. No one had ever been with a ship in here to measure the seafloor and look. We are looking into how the glaciers are doing up there. We're looking for warm water intrusion, etc. And funny enough, well, I wouldn't say funny enough, but surprisingly, no one has actually gathered this data, which we need for prediction of sea level rise, etc. So there's a lot of things for you to do if you become a geoscientist. That is my pitch. So we will hear today about the climate in the past. Climatology is a part of geoscience. That's when you connect all the spheres. You have to understand the hydrosphere, the atmosphere, the biosphere, and even the geosphere. Everything is linked together. And this is what they study when you study climatology. If we add paleo to this, it means that we're studying the climate of the past. So when we say paleoclimatology, we're looking into Earth history. Same thing with oceanography. It's also part of the geoscience. We study the ocean, currents, waves, and everything. If we add paleoceanography, we study the oceans in the past. So this you will hear a lot, or you probably see it every now and then, that you are a paleoclimatist or paleoceanographer, etc. It means simply that we look back and trying to learn from the past to look into the future. So with those, I'm actually doing this very fast, but that doesn't matter because that means that I will give Maureen Raymo here a little bit more time, which is very, very good. So with those few words on geoscience, and I hope that I convinced some of you, because we seriously need more geosciences in Sweden and internationally, but specifically in Sweden, since we don't have it in school, I felt I wanted to give a pitch, specifically also because I burned for the subject myself. So with that, I will introduce Maureen Remo, who is a professor from Lamont-Doherty in United States. It's a research center at Columbia University. And Maureen is, should I say, a paleoclimate scientist or paleoceanographer maybe? She is a fellow of the National Academy of Sciences, which is similar to our Royal Swedish Academy of Sciences. And she's also a member of Geophysical Union, and she is the first woman who got awarded the Wollaston Medal, which is a very, very prestigious medal from the Geological Society in London. And that's the most senior medal they have. But for me, Maureen is, before we met, I have used Maureen's climate reconstructions in lectures and in my research for many, many, many years, and I've cited it a lot. They're very, very famous climate reconstructions. That means that we can look back in the past and see how the Earth has gone in and out of different climate changes. And it's just an amazingly widely used reconstruction. And then Maureen do so much more than that, but that's one of the absolute most famous things. So with that, I'd like to welcome you up and give you a Crafoord lecture. Thank you.
Well, thank you, Martin. That was lovely. And I'd like to thank all my hosts for inviting me here, especially the Crafoord family. Thank you. And it's a real pleasure to be here. And so what's my talk going to be about? Obviously, climate and climate change. And I would like to start by asking the question, what can the geologic record tell us about the stability of polar ice sheets? And more to the point, what is likely to happen as we continue to dump carbon dioxide, a clear, odorless waste product, into the world's atmosphere? So I'll start by showing you what I consider to be the most famous data set from the earth sciences of all time. Greatest hits here. And this is the Keeling curve. And some of you may have seen this before. And it's named after Charles Keeling, who back in the late 50s, 1958, started making systematic measurements of the amount of CO2 in the atmosphere. And you can see that this curve has been going steadily up to the present. And the other thing you can't help but notice is these little wiggles in it. And I'll just tell you what those are. Every spring in the northern hemisphere, all the deciduous trees leaf out, make leaves through photosynthesis. And it's significant enough that it can draw down atmospheric CO2 by a few parts per million. And then every fall, the trees drop all their leaves and they oxidize and the CO2 goes back into the atmosphere. So that's the biosphere breathing in and breathing out on a seasonal basis. But superimposed on this is this long-term trend. And when I look at that trend, I see my life. I was born in 1959. In the late 70s, I went to college and I saw this curve for the first time. And at that time, and I knew that scientists were worried that the increasing levels of CO2 in the atmosphere were going to cause global warming. And nothing has changed since then, only we're just getting ever louder in our warnings about what's going to happen. So this curve, it really sets the stage for my talk. Now, I want to say one more thing. When I talk to general audiences, both students and adults have come to me afterwards and said, oh, I just don't know how to read a graph. And so here's my advice on reading graphs if you feel intimidated by graphs. I tell people, just think of this as a stock chart. Maybe this is your Apple stock or your Tesla stock. And you know how you can always click the little x-axis, this axis down here, the time axis? So you're going to look at your stock over a week or a month or a year or 5 years. So that is what I'm going to be doing throughout this talk. I'm just going to be changing this x-axis, changing the time scale over which I'm showing you the data. And I'll start right now by showing you the same data curve, but now plotted over the last 10,000 years. And this red line right here is the curve I just showed you. Okay? So now you're looking at CO2 measured both in Hawaii, and then more sporadic measurements back in time, and these measurements are from bubbles and ice cores. And so you can see that, looking at this interval right here, that really it's so obvious that at the beginning of the Industrial Revolution, the atmospheric CO2 just started skyrocketing very rapidly. And of course, this last 10,000 years, this is called the Holocene. This is the period within which human civilizations and agriculture developed and arose. Okay? So, and this change, this isn't like a few percent. This is like a 30% increase of this important greenhouse gas in the atmosphere. Okay, so where did it come from? About 90% of that increase is coming from industrial activities, primarily the combustion of fossil fuels, and about 10% of it comes from global deforestation nowadays. And where does it go? Luckily for us, it doesn't all go into the atmosphere. Only about 45% goes into the atmosphere. About a third of it is absorbed by the biosphere, especially the regrowth of forests in the northern hemisphere from the last century. And about a quarter of it goes into the ocean. This gas is just absorbed by seawater. And just as an aside, you may have heard of ocean acidification. That is what ocean acidification is. So global warming's other evil twin, okay? I won't talk any more about that, but this is obviously an important problem. So looking at this record and seeing this huge increase in CO2 in the atmosphere that we have caused, the obvious question to ask is, okay, how worried should I be? How important is CO2 in controlling Earth's temperature? So I would tell you that it's extremely important. And let's think about Earth's temperature for a minute. What controls the average temperature of this rocky planet that's circling the sun? It has no significant source of heat of its own. All the heat we get comes from the sun. Okay? And so what controls the average temperature of our planet? Basically, 3 factors. And if you're taking physics and you have the radiation chapter, you will recognize this equation. It's all very simple, the black body radiation of a planet. We don't need that, though. I just want you to think about Earth's surface temperature is being controlled by 3 knobs. And the most important is solar radiation. How much radiation from the sun hits the top of our atmosphere and can be used to heat the planet? Okay? The second knob is Earth's reflectivity. So you can see there's places, especially at the pole, that are highly reflective. You know this when you go skiing. And if that sunlight comes in, but it hits a reflective surface and is reflected back out to space by clouds or ice, it can't be used to heat the planet. So Earth's reflectivity can change. And then the last important knob is greenhouse gases. These are gases, especially CO2 and methane, that reside in the lower atmosphere. And because of their molecular structure, they can let shortwave solar radiation in, but they tend to trap the outgoing, cooler, long-wave radiation that the Earth emits when its surface heats up. And I always think about this exactly like sleeping in a cold room with a duvet in the winter, and you put on more duvet, second duvet. It's just like adding more greenhouse gases to the atmosphere. It's just going to trap more body heat under that bed, and you'll be nice and warm. So that's what's going on the Earth right now. And if I'm a geologist and thinking about this, I will tell you that every change in climate in the past can be explained by some combination of altering these knobs. For instance, when a huge volcano goes off, it increases the Earth's reflectivity because of all the sulfates in the atmosphere, and the climate gets colder. Okay? So look, I have spent my career studying Earth's climate in the past, paleoclimate. And for instance, if we go back 50 million years, we know the Earth was dramatically warmer than today. We know this. These are reconstructions of what Antarctica looked like at that time. And obviously, we know this from the fossil plants and animals that have been there. And we also know from geochemical proxies and various indirect observations that CO2 was much higher at that time. Okay, why was CO2 so much higher? It was because of tectonic processes. The Earth's plates are always moving, the interior is convecting, and the level of CO2 in the atmosphere on million-year timescales is very sensitive to the rate of volcanism and the rates of rock weathering, which can control the levels of CO2 in the atmosphere. Now, these are processes that unfold over millions of years, and the human activities right now are completely swamping these natural processes to the extent that the amount of CO2 we put into the atmosphere every year is an order of magnitude larger than the natural fluxes associated with volcanism, for instance. Okay? So we can't really look to this process to explain the current changes in CO2, but we can use this to explain changes in climate over million-year timescales. Now, you may be thinking, wait, I know climate changes on much shorter timescales naturally, and you're right, it does, because you know, and I know, there was a giant ice sheet over Sweden, and where I come from, New England, 20,000 years ago. A blink in the eye, geologically. Okay, why was that? I grew up near Boston. My technician angel and fellow Game of Thrones fan made me this figure, which is one of my favorite figures. It's the height of the ice sheet over Boston at the peak of the last ice age. And the wall in the Game of Thrones. So what's going on? Why was climate so dramatically different 20,000 years ago? So in this case, this is the first knob moving. This is the solar radiation knob that we've turned. And how have we turned it? The Earth's orbit around the sun is not perfectly circular. There's wobbles in the Earth's orbit through time, and those wobbles are caused by gravitational interactions with the large outer planets, primarily Jupiter and Saturn. And so not only does the circularity of the orbit change on timescales of about 100,000 years, the tilt of the Earth's rotational axis also changes on timescales of 40,000 years, and the precessing of the Earth on its spinning axis, like a top, also changes. So these are very predictable and systematic shifts in the Earth's orbit that cause us to be slightly closer and slightly further away, especially at high latitudes, from the sun through time, leading to very predictable changes in climate. And I'll show you a video from a paper I wrote with Ayako Abe-Oche. And this is an ice model representation of the last 400,000 years of Earth's climate. And we now know, through 30 years of research, that the waxing and waning of the ice sheets is due directly to these small perturbations, just a few percent, in the amount of incoming solar radiation that is received by the planet because of these changes in our Earth-Sun distance. There we are today. And one of the things you may have noticed there that geologists worry about is that ice sheets grow very slowly, but you can melt them and get rid of them very quickly due to these internal positive feedbacks in the system. So we can come back here today to answer our question, how important is CO2 for climate? We can ask what's going on today. Is there more solar radiation? We've been measuring solar radiation with satellites since about the mid-70s, and there is an 11-year sunspot cycle, but there's no significant long-term upward trend in solar radiation that you could point to. Is there more greenhouse gases? Absolutely. I just showed you that record, the Keeling curve, and in the context of the longer geologic record. So we are absolutely adding significant fraction of greenhouse gases to the atmosphere, and it's an important gas to control climate. And, as I'll show you in a second, if you warm the climate by putting more greenhouse gases in, what do you do to the Earth's reflectivity? Well, one thing you can do is melt back snow and ice, and that makes the planet less reflective. So again, it's a positive feedback that makes the climate even warmer. So let's connect all the dots now. Humans, fascinated with the weather. We've been measuring outside temperature and precipitation for well over 100 years. Numerous groups have gone around and compiled all the existing weather data of the world and tried to reconstruct what the mean global temperature, surface temperature of the Earth has been over the last 150 years. This is an animation from NOAA, and I'll start it right now, showing, and it's not the absolute temperature what's being shown here. What's being shown here is the deviation from the mid-century mean. So basically, as you come towards the present, this is about the mid-century. So when you hear people say there's been almost a degree Celsius of global warming in the last 120 years, that's what it looks like, and that's the data set that it's come from. And this has been reproduced by numerous research groups. And again, about 1 to 2 degrees below average and 1 to 2 degrees above average. And I'll just say, you can really clearly see the amplification of the warming that's happening at high latitudes. Probably it's due to a number of reasons, but you can probably grasp intuitively that change in snow and ice reflectivity. So let's put that short warming cycle, that short warming record on a longer time scale. Again, trying to continue to connect the dots. So I've changed the time axis now to represent the last 1,000 years. And this red record is what I just showed you in graphical form. And this red record is attached to a much longer record that has been put together by geologists studying various kinds of proxies for temperature in the past, tree rings, corals, ice core records, and including some older historical records that are more sporadic. And so again, you can clearly see that what is happening since the mid-19th century is very anomalous, okay? And also, just as an aside, if you've heard the expression the hockey stick curve, this is the hockey stick curve, okay? All right, so continuing to think about this, if we're putting more CO2 in, we see the warming that was predicted and observed. We also hear that glaciers, mountain glaciers are melting, that the ice caps are melting, that the oceans are warming up. If the oceans are warming up, they're going to expand. Heat expands water. And obviously with an ocean, it can only expand upward. And if mountain glaciers and ice sheets are melting, that water is also going in the ocean. So we should be seeing a sea level rise. Let's see what we see. So like weather stations around the world, all around the world, there are tide gauges in coastal regions around the world. Here's all the number of tide gauges in the world, northern hemisphere, southern hemisphere. It's obviously very biased to the northern hemisphere. 1940s would have been a great time to invest in tide gauges, right? So here's all the tide gauges. They've been measuring sea level for a century. What does that record look like? And this is a compilation of 4 different studies of sea level rise over the last century. This was summarized by Carleen Hay in Nature. And you can see they all consistently show that sea level is rising and also that the rate of sea level rise is accelerating. When you get back older than the 40s and there's a much more sporadic data set, the studies diverge depending on how the scientists make assumptions about how to interpret the data. But clearly, post mid-century, these studies all come into agreement and also show, if you look at the average rate of rise over the whole century, it's about 1.5 millimeters per year, and the rate now is 3 millimeters per year. So that rate is accelerating. Let's change our time axis again and look at this record over 2,000 years. And the record I just showed you is right in here, basically the 20-centimeter rise right in there. And this is a reconstruction of sea level by Alan Kemp from the east coast of the United States, based on plants and animals in tidal marsh zones. And you can see, again, this very characteristic hockey stick. What we are seeing now is anomalous. Every piece of this puzzle makes physical sense and is observed. So, what do I know for sure? I know that climate is changing naturally all the time. And I also know that very small variations in incoming solar radiation, in the Earth's reflectivity, and in greenhouse gas concentrations can lead to large and sometimes rapid changes in climate. And you see this throughout the geologic record. It is inescapable to me that the conclusion that the activities of 7 billion people can certainly cause changes of this magnitude, and are. Okay? So let's circle back to the ice sheets now and think about sea level for a minute. There's an ice sheet on Greenland. There's a much larger ice sheet on Antarctica. What do these numbers mean right here? If you melted each of those ice sheets and just spread that water evenly across the ocean, that is how much sea level would rise by globally, okay? And of course, this is the big worry that scientists all around the world, polar researchers, are thinking about right now. What is happening to the polar ice sheets? And here's how you should think about the polar ice sheets. Think about a frozen lasagna, right? And you've preheated the oven, and the atmosphere is the oven that we have preheated. And the ice sheets are like frozen lasagnas. You put it in the oven, it's not going to defrost instantly. It takes time, right? So even if you could magically just stop everything today, global warming, the addition of CO2 to the atmosphere, those ice sheets are going to continue to defrost and melt and put sea level into the water. And this put water into the ocean, causing sea level rise. So these are the questions we're asking right now. How much will seas rise? How fast will they rise? How will the rise vary regionally? And one of the most important things that this scientific information can inform, of course, is how can communities best respond to rising seas. Now, there's a huge group at where I work that studies Antarctica, both around the coastal regions and on land. And this is a video of the mass loss of ice in Antarctica from 2003 to 2013. Here, I'll run that again. And based on satellite measurements. And it's very, very clear that there's ice mass loss in especially West Antarctica in this region and also the Antarctic Peninsula. But what's interesting here is you can also see there's places that are gaining mass in Antarctica. And in fact, if you look at this plot of, oops, it's cut off a little bit, sorry, but this is basically mass and loss in gigatons of ice. You can see that West Antarctica is losing mass. The Antarctic Peninsula is losing less mass, but even the direction of mass, the ice mass in East Antarctica is uncertain. Maybe it's gaining mass, maybe it's losing mass. It's very uncertain what's going on in East Antarctica right now, and it's probably one of the most understudied and inaccessible regions in the world. So what do we do? Now, this is a real talking point for climate deniers. They say, look, Antarctica is so cold that if you warm it a little bit, there'll be way more snow in Antarctica, and that the gain in snow in East Antarctica will offset losses elsewhere, so we don't have to worry about sea level. Okay? There you go. Well, that's a reasonable hypothesis. How do we test that? I don't think they're interested in testing it, but as a scientist, I'm interested in testing that hypothesis. So one of the projects that we do in my lab, one of the things we've done is pivot to study sea level in the past. And in particular, we're asking the question, what did a modest warming do to ice sheets in the past? Now here, this is the last 450,000 years of climate. These are temperature records from ice cores in Antarctica. Here's today, right here. And here's the last time it was warmer than today, 125,000 years ago, an interval also referred to as the Eemian. And at the peak of the Eemian, it was 1 to 2 degrees warmer relative to pre-industrial. So, you know, it's kind of like where we're going very quickly, okay? Now, thinking back to our knobs, why was it warmer? It was warmer because Earth's precession was in a position where the high latitudes were pointing a little closer to the sun. So it was more solar radiation received at high latitudes. So we are focused on this interval, and we're asking the question, how did the ice sheets respond at that time? Okay. How do we reconstruct sea level in the past? We're geologists, we go out in the field. Right now, this is me and my postdoc, and we are standing on a fossil reef that is almost 100 kilometers long. And right out here is the modern reef. That's the Ningaloo Reef in northwestern Australia. You can go and you can see the fossilized corals in the field. They're spectacular. Sometimes you hit a real jackpot. This is a 3-million-year-old shoreline where we found fossil oysters with fossil barnacles on the fossil oysters. I mean, that's like, oh man, look what you found. That's amazing. Like, you know you're at sea level when you find something like that. Okay, but here's an even more, one that might bring it home even more in terms of like sea level in the past. Here's a Landsat image of Miami. It's Miami Beach right here. And this is called a bare earth LiDAR, which means it's an elevation satellite map of the surface, but all the buildings and vegetation have been taken off. And what you can see is that there's this long ridge, and with this high ridge through the Miami region that's up to 5 meters high in elevation. And you can also see these little channels that are going through this ridge. This ridge is made completely of subtidal carbonate sands. So these are sands that formed under the sea surface, in particular oolites. And here's the modern analogy. This is the tip of Eleuthera, which is one of the islands in the Bahamas. And these are these subtidal sands where the tidal channels are going on and off the bank. So if you look at Miami, you would think, and they date to 125,000 years ago, you would think, oh my goodness, Miami was completely underwater, and it was. And you may say, oh my God, sea level must have been at least 5 meters high. And I would say, you're close, But here's the cool thing that we've learned over the last 10 years in studying research and studying sea level in the past. And that is when I learned how to study sea level in the past, it was like you went out, you found a nice stable part of the world, no volcanoes or anything, and you just looked at where that fossil shoreline was and considered it like a bathtub ring. And you considered the ocean basin to be like this stone tub. Well, we now know that's obsolete. We now know that everywhere you go around the planet, the Earth's surface is also moving, okay? And now, you guys are all in Scandinavia here. You absolutely know that when you load the ice on the land depresses, and you take the ice away, and the land's rebounding, which is one of the reasons why sea level is not such a big deal, sea level rise in this region, because this whole region's still rebounding from the removal of the last ice sheet. But the point I want to make, even though it's very obvious where ice sheets are, that all over the world, the land is still moving and responding to the loading and unloading of ice sheets and the redistribution of water associated with the ice sheets since the last glacial. So if you're looking at Miami, you have to ask, well, where's the land been moving since that time? So not only is the bathtub always deforming, here's the other thing. The water is never flat. Picture this as Greenland. Right now, Greenland. Up that way? Not sure, I'm a little disoriented. Greenland is so massive, it actually acts as a gravitational force pulling the ocean water towards it. When I learned this about 10 years ago, I was like, oh man, that's so cool. Who would have thought that? So if you could just immediately melt all of Greenland and put it into the ocean, sea level in most places in the world would rise by 5 meters. But within like 800 kilometers of Greenland, sea level would fall by tens of meters because of the loss of that gravitational attraction. So now all of a sudden you're getting a sense of like, okay, maybe those scientists are earning their keep. They're figuring out a lot of cool things about this problem that's pretty complicated, right? So this is exactly what we've been doing in my lab and others' lab. We have a big project called the Pliomac project that I just want to plug for a second. It's a group of climate modelers, geophysicists looking at Earth deformation, and field geologists, and we're out trying to reconstruct sea level, not only in the recent past, but in the deep past, to try to provide the constraints that climate ice sheet models need to calibrate themselves, to see if they're doing a good job. I want to just show you one record that we have submitted right now from Blake Dyer. He's my postdoc. He just accepted an assistant professor position at the University of Victoria in British Columbia. I love this picture. He's sharpening his machete in the back of the van as we're on our way to do field work in the Bahamas. And that's like not all like on beaches. It's mostly in the jungle. And here's what this now is 118 to 128,000 years ago. That is that Eemian window, that window of the last interglacial that was warmer than today. And our reconstruction of sea level at that time, based on fossil corals in the Bahamas, is that sea level was 3 to 4 meters higher than today at that time. Okay? So that is corrected for the land deformation that I implied when I talked about Miami there, okay? So this is also interesting because this is significantly lower than the 6 to 9 meters that's cited in the IPCC reports. And again, it's because we're getting a better handle on the Earth movements, the mantle viscosity, and the other factors that can contribute to the deformation of shorelines on long time scales. Okay, so where does this come, how does this compare to where we're going? So we say it was 4 meters higher. Last time it was 1 to 2 degrees warmer than today. How does this compare to where we're going? So here's recent projection of sea level in 2100 from the US National Climate Assessment, which came out last year. And you know, this is not, sorry about the feet. You know why there's feet there, right? Because we're like the only major nation that's not on the metric system. But you can see that, you know, I mean, 2 meters, right? You know, it's completely reasonable and consistent with it ultimately topping out at 4 meters. But here's the thing. Clearly, what you see here is a huge range of uncertainty in what sea level is going to do over the next 80 to 100 years, and obviously beyond. What is that uncertainty caused by, and what does it do to? Well, part of it is due to our, you know, lack of complete understanding of the physics of ice sheets and how they're going to respond. But the biggest part of this uncertainty and where we're going to be 80 years from now comes from what we do now and what we choose to do now. It comes from an uncertainty in what the emissions pathway of CO2 addition to the atmosphere is going to be. Okay? So if we do everything right, transition quickly to a, you know, non-carbon-based economy, we could be down here. If we just continue on the business as usual pathway, I feel completely confident we will easily break 1 meter to 2 meters by the end of this century. And you know, that's obviously a gut feeling shared by numerous other scientists around the world. So in thinking about this, how do you even think about this? I think about this like, okay, wow, maybe we can keep it under a foot. But even that would be an incredible, like, just terrible thing to happen around the world. Because you think about what's happened now. We've already had anywhere from 1/2 to a foot of sea level rise in many places. Here's Miami. Miami today is constantly being flooded by king tides and nuisance tides. And it's just one characteristic of many towns and communities up and down the East Coast. They are spending hundreds of millions of dollars to try to keep the water out. The problem is they can't build a wall because the land is so porous. The limestone Miami is built on is so porous, the water just comes up through the ground. Sea level is also already having a huge negative impact in these towns and in these communities. Here's another example of how sea level is already having a devastating impact around the world. This is from right where I live, New York and New Jersey. A few years ago, Hurricane Superstorm Sandy hit. The storm surge hit on high tide. That high tide is a foot higher than it would have been 100 years ago because of global warming-induced sea level rise. So obviously, climate change is already making storms and hurricanes more devastating. And imagine just adding more on top of that. And then finally, there's even like bigger issues, global issues to think about in terms of sea level rise. And that is the island nations, for instance. This is Male, it's the capital of the Maldives. On this island alone, there's about 325,000 people on an island that is about 1.5 meters above sea level. So how do you process something like that? I don't even know. I mean, these are, and this is just one of dozens of island nations around the world, right, in communities that are literally at risk of losing their sovereignty because of activities that they really had no part of and didn't really contribute to in any significant way. So this is a really, really, it is an existential issue. It's an issue of climate justice. It's an issue that we all need to be aware of and think about. Now, I used to stop my talk right about here and just say, we got to solve this problem. This is critical. And you know, we can't afford to not think about sea level rise and the potential impact of sea level rise around the world. And I typically would get 2 questions back. And they were like, aren't you just depressed all the time? This just seems so hopeless. And then the other question I would get is, oh my God, what can I do? And obviously that's a great question, what can I do? And I realized after a while that I needed to like add some more to the end of my talk. So I have 5 more slides. And I'm going to take off my scientist hat right now, and I'm going to put on my fellow citizen like you hat, one who knows a lot about climate. Okay, and just think about this for a minute. The climate problem is a huge, all-encompassing problem, and it's real. I hope I just helped you connect the dots to every single part of this problem that's happening. And it's not a problem that's going to be solved by like some magic geoengineering fix or a machine that can suck CO2 out of the atmosphere. And it's not going to be solved by like you deciding not to fly somewhere and you deciding I'm not going to buy any new clothes in 2020, right? It's not going to happen that way. It's a problem that's going to require all hands on deck. It's going to require communities. It's going to require individuals. It's going to require state, local, national governments. Most importantly, it's going to require the business and finance sectors of the world to really get involved and embrace solutions to this problem. And I am very optimistic because I think all those things are happening right now. And in fact, I know there are tipping points in the climate system, but I believe there are also tipping points in societies. And I believe we are like almost in the middle of a tipping point right now. So, however, what do we do as individuals? And I will tell you what the advice I would share with you. I tell people to think about their friend Bev. Okay? This is my friend Bev, Beverly Sellers. She is an activist. She's a writer. She's the former chief of the Hatchall First Nation of British Columbia. She's one of my heroes. But more to the point here, what does BEV stand for? BEV stands for Buy, Educate, Vote. Okay? So this is buy. We can all do this. We can all buy thoughtfully. We can all buy sustainably. We can all be conscious of our energy, food, and transportation choices. You know, we can consume less stuff. Okay? One of my pet projects is beef. Eat less beef. In fact, I've worked on a project over the last few years with a group of students at Columbia University. The students made a website, holdthebeef.org. I encourage you to check it out. But here's some data that from our group, Gidon Ishal. And what's shown here is the greenhouse gas emissions that you get for making 1,000 calories of beef, like 1,000 calories of beef. And you can see it's huge. Here's beef, chicken, pork, eggs, dairy, legumes. Here's the freshwater use, land use, and fertilizer pollution. So if I leave you with anything today, it's eat less beef, okay? Educate, E. There's many places to get lots of high-quality information about the climate change problem. And we're all on a journey. I learn so much every month about climate change. It's such a huge, huge issue. And I just want to share a few of the issues, a few of the stories that have really made me feel good about our future and what's possible. I love this one. There are whole communities around our nation. Here's one in Texas that have converted 100% to renewable electricity. I love the irony here. They doing it to save cash, not the planet. Okay, I'll take it. Renewables, wind and solar, are now financially competitive with fossil fuels around the world. Costa Rica, one of many nations, have set really ambitious goals to convert away from fossil fuels. Their electricity is now almost entirely from renewable resources. There is one country in the world that is carbon neutral. I'll leave it to you to guess what country that is. At Columbia, we have a group that is working on methodologies to take CO2 out of the atmosphere and put it into the Earth's crust and turn it to stone. Again, this is just part of the quilt of solutions we're going to need to solve this problem. Many clever engineering developments that are happening. I am heartened by the fact that many different groups are beginning to use the legal system to fight climate change. And this particular one is our Children's Trust lawsuit that started during the Obama era. It was a group of about 15 teenagers that are suing the US government to act on behalf of their future to stop climate change. It's now at the Supreme Court in Oregon, the state Supreme Court. Expect it'll eventually end up at the US Supreme Court. Buildings. So I'm a geologist. I am a member. My professional organization is the American Geophysical Union. I pay my annual dues. The AGU bought a 25-year-old office building as its new headquarters in Washington, D.C. a few years ago, and they converted that building to a net carbon zero building, renovated it, and it is the first one in Washington, D.C. I don't know how they did that with our dues, but if a bunch of geeky geologists can do this with their organization, I say anybody can do this. And here at Columbia University, in 2006, our university set a goal for 35% reduction in emissions by 2020. We passed that goal last year, and we're now in the process of setting our new renewable goals with the ultimate goal of being a net carbon, a zero carbon campus. So, oh, wait, I have one more I forgot I added. I'm also incredibly heartened by the level of student activism I see around the world right now. And this is something that's really just exploded in the last 2 years. This is Laura, Clara, Kai. All three are working on advanced degrees in climate science at Columbia University. And of course, I cannot end without putting up a picture of Greta Thunberg, who has been hugely instrumental in inspiring students and her peers around the world, and grown-ups, I might add as well. So that's educate. We're all on a journey. We should learn as much as we can about the climate problem. It is so vast, nobody can master it all, but educate yourselves, then educate your family, then educate your friends and your communities. And then last, V stands for vote, right? I hope, well, maybe all of you can't vote yet, but vote, vote, vote. So with that, I will stop, and thank you for listening. Thanks. Thank you. Good?
Oh, thank you. Thank you so much.
Thanks.
We're going to save all the questions because we're going to have a panel here in the end where we can continue to discuss all these issues that have been brought up and climate science, etc. So thanks, Maureen.
Thank you.
Thanks a lot.
Okay.
And now I invite the next speaker here, who is Raimund Muscheler. Did I pronounce it right? And Raimund is a professor of quaternary geologist, but someone here just, actually your becoming moderator said that he was the professor of the sun, so I think that's easier to say. So Raimund is actually going to dive in to the details about the sun. He's really, really an expert on this, so it's my pleasure to invite Raimund on the stage.
Thanks a lot. Yes, thanks a lot. Is that okay? Yeah, so I'm here at Lund University at the Department of Geology, and if you don't know, quaternary is the geology of the last 2.6 million years. So what I'm doing is I'm looking at ice cores, I'm trying to get the solar signal back in time and to study solar relationships with climate. So there will be a little, not so much about my research, but more like a review of what we are knowing today. So I want to start to tell you a little bit about our star, the sun, show you some examples for the solar influence on climate, and then focus on the discussion, what has the sun to do with recent climate change? And you saw already a bit from Maureen. I will go into a bit more details. So if you look at the sun, And there are amazing videos you can download from the NASA SDO homepage. We have satellites today. They look at the sun all the time. And what you see when you look at the sun, you see the solar rotation, you see spots on the sun, you see spots changing, growing, and decaying. So what you basically see is the sun is not the constant lamp up there. The sun is changing, and that means the impact on Earth does also change. And what do we know about the sun of direct observations? So what I'm showing here is the sunspot record. This is the last 400 years about. And you have a sunspot number. So these are counts that people did. They looked at the sun. They counted how many sunspots there are. We have different records, the sunspot number and the group sunspot number. More or less, they agree. And what you see is when people started to look at the sun with a telescope, so the telescope is now about 400 years old, and Galileo looked at the sun, for example, painted the spots on the sun. So we have these sunspot informations. And you see the sunspot change in time. We have an 11-year cycle, so every 11th year we have almost no sunspots, and then we have the active sun again and no sunspots. And what you also see is there are long-term changes. So you have periods of very low solar activity and periods of very high solar activity. So for example, this we call the Maunder minimum, the Dalton minimum. And what you see, the last 50 or so years, we had very high solar activity. And that's why it's important for climate, the discussion of climate change. Only for the last 40 years, we have actually satellites looking at the sun. So really measurements of how much energy we get from the sun, and that's the important component. So if we get more energy from the sun, Earth warms up. If we get less energy from the sun, Earth will cool down. But we have only data for the last 40 years. And that's how it looks. You saw this picture in Maureen's talk, more or less. There are slight differences depending on people looking at the data. But what you see is, you see the solar 11-year cycle. So every 11 years, we have high solar activity. We have a lot of sunspots. And we get, since there are bright regions around the sunspots, we get more energy from the sun. And then, when the sun is quiet, like it is today, we get less energy from the sun. Important in this context is these changes are small, 1 per mil about. Yeah? No, it doesn't seem to. Yeah, no. Okay, so this is the background. The sun changes, we get more or less energy from the sun, so we do expect that the sun influences climate. The question is how much? What we can do is we have climate models, we have the solar input to Earth, we can put the energy from the sun into the climate models, we can change this energy from the sun, and if we do that, 1 per mil increase in energy from the sun that we know can happen, we get 0.2 degrees Celsius higher temperatures. So that's not really disputed, that's pretty straightforward. And now we can look at the sunspot record. And what we have from the ice cores is longer records. And we know all of this period from about 1400 to 1850. It was relatively cold globally. So we call this period the Little Ice Age. Glaciers advanced. And yeah, on average it was colder. And we have documents also showing this nicely. So this is just an example. This is a market on Thames River in 1814. So the river was frozen. They had markets on this river. They had it back in time, but that was the last one in 1814. Since then, it did not happen again, that the ice was frozen enough for this. You know, we have all these examples of climate change. We have the glacier retreating, so we see the global warming. I show this because if we go back in time, we see similar things. We can reconstruct solar activity, we can reconstruct glacier advances and retreats, and many examples from the paleoclimate, so last 10,000 years or so, they show similar linkages, that with lower solar activity, glaciers grow and retreat with higher solar activity. But we have a problem. So with 1 per mil change in total solar radiance, we cannot explain a lot of climate change. It's 0.2 degrees Celsius. We don't know how bright was the sun during the monominimum. So that's another question. And there are suggestions that it's not only the energy from the sun, it could be other processes. The sun determines how much cosmic rays come to Earth, and they could produce clouds, and then they could change how much energy stays at Earth. So this could be an amplifying process. But these are still open questions, still being researched. But even though we can say something about what has the sun to do with recent climate change. So this is the global temperature of the last 150 years. 1850, 2020. What you see is global warming. And you see also it came in 2 steps. So around from 1900 to 1940, it was about ½ degree temperature increase. From about 1970 to today, a bit more than ½ degree increase. That's what we know. We know this one we can easily explain by the sun. Not really easily, much more. So we can now compare the temperature curve with a solar curve. So just assume we don't know anything about the sun but sunspots. We know low sunspot number, so the red one here is just the 11-year average. You see the 11-year cycle, but the thick line is just the average solar activity. We know solar activity increased from 1900 to 1940, so it has the potential to explain part of the warming. We know it has been relatively stable from 1940 to 1980 and high, and that actually also agrees pretty well with more stable temperatures. But if we look at the last 40 years, you obviously see that temperatures went up and the sun solar activity went down. And we are actually now in a period of relatively low solar activity. So we are on levels today as we have been around 1900. So just from this graph, no matter how the sun influences climate, you cannot claim that this warming here has been due to the sun. So I would conclude the global warming of the past 30 to 40 years cannot be explained with solar forcing. Just, I don't see how that could be possible. However, climate skeptics, people who question kind of the causes behind climate change, they still use the sun to create doubt. So you hear phrases like, it's all natural, temperatures always went up and down, and could be the sun. And so, for example, you see that was in 2011 in Aftonbladet. You got a big headline saying the sun on low activity could create a new ice age. Completely unfounded by anything we know. And it has effect on people. So this, in Sydsvenskan, they published a study saying a lot of decision makers say that we don't really trust the results from climate research. And some say we don't accept that there is a risk. And so what I would say is, you have all right to be skeptical, but you shouldn't have the right to be stupid if you are deciding about our future. Okay, that's Sun today. Thank you. And one last thing, I would also thank the Crafoord Foundation for organizing or for initiating and supporting this event, and also for supporting climate research in general. So the Crafoord Foundation supports, for example, the Swedish contribution to a new ice core project, where we will hopefully get ice of the last 1.5 million years, where we can get the atmosphere in the bubbles that existed on Earth 1.5 million years ago to better understand how climate changed in the past. Thank you.